Okay, let's get on to looking at the trapezoidal rule. So, important things to note, the trapezoidal rule gives you an approximation for the area, whereas calculus gives you an exact value for the area. So, in this approximation, obviously, the more trapeziums that we created, the more accurate, or the closer we get to the real value, the more accurate our answer would be. However, so obviously here in this example, if we calculated the area of each one of these trapeziums and added it all together, we would have our approximation for the area under this curve from 0 to 3. And the area of a trapezium, remember, is a half. I'll just call it A plus BH. You'll probably see it as written as H on 2, A plus B, where H is the distance between your parallel lines, and these are our parallel lines, and they're also our A and our B. Now, the way that you will often see the trapezoidal rule written, it's much more complicated. It's much more complicated. The reason being there is a pattern, and it's in recognizing features of the pattern that you're able to write a formula that covers not just breaking it into one strip or two strips or three strips, three trapeziums, as is in this demonstration, but they talk about n strips. Now, in doing that, it does give you a general formula, but like I said, on first glance, that can look daunting and very confusing. So let's just start at the beginning and develop our understanding of this, which will then lead us to a more generalized formula. The interesting thing is that on the reference sheet, they actually just leave it with one application, and I find that interesting. Oh, and by the way, this terminology, one application, just means they're just taking the region and they're making one trapezium. Obviously, the diagram back here, we would say that had 3 applications of the trapezoidal rule. That just means we've broken the region into 3 trapeziums. So you can see here in this example here, the area under this unusual curve has been approximated by the area generated by this trapezium, and just one trapezium. You can see here we've got the area is the H on 2, where H is, in this case, H is x2 minus x1. It's that distance between there. Now, we don't usually call them x1 and x2. Remember, we would have called them from A to B. We would have wanted the area from A to B. So you will see a variation, and in particular on your reference sheet, reference to B minus A. It's the same as x2 minus x1 could be replaced with B minus A. B minus A, as you can see, like I said here. The 2 comes from our understanding that we need a 2 in our area of a trapezium. Function 1 is what we would normally call A back in our H on 2, A plus B. This is really confusing, isn't it? Because now I'm using not A and B as values on our integral. We'd normally go A to B. Now I'm using A and B, and we have for so long, as actual function values. The height of the function in this case, it would be the height of the function at x1. That was what we'd normally call A. We're going to go back to a little bit of function notation and call it F1, or as you can see here, it's called FA. Now, look, I think the most, like I said before, yes, this is going to be confusing, but it's confusing because there are different ways of writing the exact same thing, just different methods of writing the same thing. So if you need to just keep pausing or rewinding, then please do that. Don't keep going if you're confused. Worst thing you can do. Stop it, stop the video, rewind, listen again, and if you're still confused, just totally stop and ask me about it in class. So I'll assume that you're going okay, and I'll talk now about what you actually see on your reference sheet. So it's going to say that the integral from a to b of f of x dx, this is in calculating the area, is approximately equal to, and notice the approximately equal sign they use, the b minus a, because that is actually the values from our understanding from here. The b and the a are our x values. So from a to b, and divide that by 2 because of the formula I said for area of a trapezium. F of a, because that is the length of one of the parallel sides, plus f of b, because that's the length of the other parallel side in the trapezium. Now, as it says, to increase the accuracy, more strips are introduced. Yeah, that makes sense. Now, when it becomes really confusing is when you see something like this, that the area is approximately, and that's just another symbol for approximately equal to, half of h, f of a plus f of b, etc., etc. I might just go to a blank sheet and then talk about where this actually comes from. So what I've done here is I've drawn the function 3 times, so under this curve, under this curve, under this curve. In this example 1, I've just divided it into 2 trapeziums. Example 2, I've divided into 1, 2, 3 trapeziums. Example 3, I've now got 1, 2, 3, 4. Now, with maths, and the reason that mathematicians were able to develop concepts was because they identified patterns. It's as much about identifying patterns as it is about the process. So there wouldn't be a process if somebody hadn't identified a pattern. And sometimes that's what you have to do when you look at a question. You have to look at it and go, oh, I recognize this pattern, or I can see something here, I recognize it, and you make a connection to some maths that you know. Don't underestimate the importance of being able to see a pattern. Okay. And like I just said, you know, the fact that you can see a pattern sometimes connects you to the correct process because you've somewhere before seen a variation of that pattern, or you've seen a question that required a little bit of that pattern. So yeah, being able to see patterns is critical in maths. So with the first one, you can see that to get the area of this, we're going to add together the area of trapezium twice. So that's all this is. And what I've done in my notation, I'll go back to blue pen. What I've done is I've called this distance here in our trapezium f of a, because a is your x value. H units away is, I've just called it now x1. You might see it written as a plus h. Well, that's what the x value there would be. But I'm just calling it x1 for simplicity. And then I've called this is the outer limit. It's f of b. So we want the parallel sides for the first one, which are f of a and f of x1. And for the second trapezium, f of x1 and f of b. Now, I've taken adjunct 2 out of these two terms, put it out the front, and I'll have f of a, f of x1, f of x1, plus f of b. What do you notice? This is the pattern thing. What do you notice? Hopefully you notice there are two of those, and I'm going to write it as h of 2 outside of my f of a and my f of b, because I know the pattern. I know the pattern. And two of those, and I've strategically placed that here with this one because, like I said, I know the pattern. Let's move on. When we've got 3 strips, so we will have, now the important things to note is the size of H has changed. H is smaller here than it was over here. So if I had 3 strips, I'd have a different value for H. I'm calling my first parallel line of my trapezium f of a. The second one, I'm calling it f of whatever the first x value after that is. Second x value, and that's all I've got except for the last value for x, which is b. So we've got f of b. Setting them up now, you can see 1 trapezium, 2 trapeziums, 3 trapeziums. Now, taking h on 2 out, just as I did there, I'd have f of a, I've accounted for that, f of x1. Going on to the next one is f of x1 plus f of x2. Then taking h on 2 out of this one, I've got f of x2 plus f of b. Now, like I said, because I know the pattern, I'm going to put my f of a and my f of b at the beginning. Why? Because they don't occur anywhere else. If I look at f of x1, it occurs again here. F of x1, f of x1. I can see I've got 2 lots of f of x1, but I've got an f of x2 and an f of x2. So I've got 2 lots of those as well. So my pattern becomes h on 2, f of a plus f of b plus, and I'm going to take the 2 out of this, 2 lots of f of whatever the x1 value was and the x2 value. Any similarities between this and this? Well, yes, we've got h on 2, we've got f of a, we've got f of b, f of b. Here we had 2 times only one x value, whereas here we've got 2 times these 2 values. I'm going to pause the video and write up the next one and then come back and talk about it. So what I've done is, and scroll back, you can see that I'm going to have 4 applications of the trapezoidal rule. 4 times I'm going to use the trapezoidal rule. Here they are. 1, 2, 3, 4. Take your time, pause the video, have a good look at that. What you'll see is h on 2 is common and I'm taking that out. You'll see when I'm taking that out, I've got an F1 and an F1. So again, you can see that I'm getting this 2 times f of x1. But if I go a little bit further, you can see that I'll end up with 2 f of x2s, 2 f of x3s, and only 1 f of b. So there was only 1 f of a, 1 f of b, and I'm going to put them at the front. Why? Because, like I said, I know the pattern, and it suits the pattern to set it up like that. And so my pattern looks like this. Now, similarities. Yes, we've got the h on 2, the h on 2. We've got f of a, f of a, f of a, f of b, f of b, f of b. And 2 times those 3 values in between. I'll stop the video there and talk more about patterns in the next video.